All right, moving on. Part 2. We have a cube and the diagonal of the cube. Okay, so these are kind of hard to see. Hope I can draw this relatively nicely with my tablet toy. Okay. Yeah, so cube counts like this, and by definition, cube, which I don't know, I haven't really dealt with too much because they're kind of simple. By definition, all these sides have to be exactly the same length. Now, I don't know if I need to use x here because it talks about another cube. Oh yeah, I can't call this x, can I? It says the diagonal is x. Well, what do they mean by diagonal? Diagonal, they mean the distance from right here to way back opposite corner, as completely far away as you can possibly get inside the cube over there. So it's going through the middle of the cube, so I'm going to draw it that way. And draw and say that's similar to another one. You know, I'm going to cheat and draw my similar one like this. I'm going to select this image, copy paste, and then can I grab this? Oh, cool. And then this one, I'll grow bigger. Okay, so we have two cubes and they're similar. Basically, that's what similarity means. You know, that's actually not a bad way to show you what similarity means. When you grab something and grow it, or you change the font on something, that's pretty much what similarity is. And now we're talking about figures like this, and we're looking at area. All right, so the diagonal of this one, so am I still in blue? This length is x. This length is x square root 3. How mean is that? All right. Then we also know this volume over here is 64. So the question is, what's the volume over here? Well, you could spend a lot of time trying to figure out if this volume is 64. Actually, it's not too hard. If this volume is 64, what's the length of this side? If this volume is, if you could figure out the length of this side, you could solve this for x. You could figure out what x is, and from that x, you could figure out the length of this side. That's crazy talk. There's a much easier way to do it. Since I know these things are similar, again, I'm trying to figure out what is it that I multiply this x by to get that x, or sorry, this length. This diagonal, even though it's not a standard measurement on the cube, it is a linear measurement we can use to compare the two cubes. I know that a length over here becomes so much longer when it becomes a length over here. And when I say becomes so much longer, I mean by a multiplier. So I know that stuff over here, I'm going to use a different color yet. How about orange? When I multiply this thing, I keep doing my little arrows here, it got multiplied. That's not an x, that's a multiply. It got multiplied by the square root of 3 to get longer. So I know that k is the square root of 3. The stuff, any length on this thing, if these are really similar, remember every length is in the same ratio, including lengths of sides, and those are the building blocks of volume. Any length over here becomes square root of 3 times longer when I move it to the larger cube. When I did that little zoom, when I did my copy paste, I enlarged all the lengths by a multiplier scale factor of square root of 3. So that's my linear scale factor, that's k. I need to translate between this volume and this volume, though not on the k channel, but on the k cubed channel, which is kind of a mess here because what's the square root of 3 cubed? It ain't pretty. It's not 3 or 9 or 6 or any nice number like that. The square root of 3 times the square root of 3 is 3, then times another square root of 3, well, it's just kind of like 3 times the square root of 3. It's not really... Is that right? 3 times the square root of 3. Square root of 3 times square root of 3 is 3 times square root of 3 is, yeah, it's a lot of 3's. You can leave it like this or you can write it that way. It's fine either way. So that's k cubed. That's the way volumes happen. I know that this volume is this little volume times 3 times the square root of 3. Let me write that again. Let me go back over to red. This volume, and let me call it little v. Little v times 3 times the square root of 3 equals 64. And that's what I'm trying to find here. So little v is just 64 divided by all that junk. And that's it. I can stop right there. It's 64 divided by 3 times the square root of 3. Okay, see, I told you they got harder. All right, last one. Base areas of two similar prisms are 32 and 200, respectively. Find the ratio of their lengths and the volume of their larger prism. So ratio of their lengths, I'm going to call that k, essentially. That's the ratio of lengths. And the volume of the larger prism, if the volume of the smaller prism is 150. Okay, let's get some similar prisms up here. Now, I don't know what shape these prisms are. They might be pentagons. Of course, I had to make my life hard. Let's just pretend these are pentagons. We got pentagonal prisms. We have a small one, and we have a big one. I'm going to do the same thing I did last time. I'm going to take that. Yeah, that's everything I need to change, right? So I'm going to take that one. I'm going to go copy, paste. I'm going to move this one over here, and I'm going to cheat. Whoop, look, that's perfectly similar. Okay, great. So I know that this this base area down here, this base area, and that's an area, is 32. The base area down here is 200. So if I was just supposed to say to take that ratio, 200, whoa, I said 200. 200 divided by 32, what am I finding? Well, 200 divided by 32, that's area divided by area. That's going to tell me what k squared is. Oh, let's reduce that. We could make a nicer fraction out of that. 200 divided by 32, that's 25 fourths. Oh, that's coincidentally pretty, isn't it? So that's 25 fourths. 25 fourths is k squared. Well, if 25 fourths is k squared, guess what k is? And I need to define k for this question. K is the square root of 25 fourths. Square root of 25 fourths is 5 halves. That's lovely. So k is 5 halves. Any length over here gets multiplied by 5 halves when I take it over here. Or any length over here is 5 halves times longer than that. It's 2.5 times longer. So what do I do if the volume of over here is 150? How do I find volume over here? Well, I just have to take, when I take this on this little trip over here, I have to multiply 150, not times k, but times, because we're talking about volumes. To transform a volume, I have to take it times that cubed. So let's go back out here. Let's take, if you want to take 5 halves and cube it, here's an interesting way to do it. Take 5 halves like that, and then outside the parentheses, let's take it to the power of 3. I get 125 over 8. And I'm supposed to take that times 150. And I get a nice number like 9375 over 4, which is that. These aren't pretty. I'm going to cheat again. No, I'm not. I'll just pause. Yeah, and that's the volume of that thing. I'm toying with the idea of giving an alternate method. If you're satisfied with that, go ahead and stop the video right now. If you're interested in another alternate method, go ahead and continue. Let me set that up. All right, warning, warning, warning. Alternate method. That's why I highlighted this thing up here. So if someone comes and asks me a question, I'm going to say, oh, you're talking about the alternate method. That's weird. Okay, so you can actually use this. Okay, remember how before I was saying you can't just say, oh yeah, x is to 7 like 72 is to 50. That won't work. Yeah, that doesn't work. But the reason it doesn't work is because this is supposed to be the ratio of lengths, and this is the ratio of areas. In other words, this thing right now is k, and I'm bringing it over. This thing over here is k squared. Well, this would be repaired, or we could use this thing if we could just square everything on this side. Then we'd have an equality that works. So take a look at this. This actually works. If I square everything on this side, now I have a proportion that I could actually use with cross multiplying, and it would work. It's kind of a nightmare. First of all, let me reduce the 72 over 50. The 72 over 50, I think, whoa, how come I didn't get my calculator? I think that reduced, didn't it? 72 over 50. Oh, it did when I square rooted it. Yeah, it's 36 over 25. So let's just call that 36 over 25. But that's no big deal. You've done that before. So now I'm saying 25x squared equals 7 squared times 36. Now we get much bigger numbers this way. 7 squared times 36 divided. 7 squared times 36, 49 times 36, and I'm going to have to divide that by 25. I get x squared, so to get x, I'm going to do this fast because it's alternate method. I take the square root of that, and I get 42 over 5. So let me write down what I just did there. X squared equals 49 times 36 over 25. And then you square root both sides, you get x equals 42 over 5. When I did the old method on this problem, I got x equals 42 over 5 up here, so I could do that. Let me do that with one of these volume ones. Let me do it with the Panda Bear one, just a second. So again, I'm going to have this big red warning label at the top. Alternate method. All right, so this one had a height of 16, this had a height of 12. So I could say 12 is to 16 as, and this was area also, right? Smaller is to larger. Well, this is areas. So this is already k squared. These are just k's. To make them agree, I got to raise these to the squared power. Okay, well this is kind of a pain because what's 12 squared? I mean, these numbers start to get huge. This is 144 over 256. This equals 40 over x. I could, let's say next step would be 144x equals, oh my gosh, 40 times 256. Numbers are big, but you know what? It works. So what's 40 times 256 divided by 144? 40 times 256 divided by 144. I get 640 over 9. Oh, you know what? That looks kind of familiar. I get 640 over 9. Is that the same thing we got before? I believe it is. If I have time, I'm going to do one more of these that uses a volume, because the volume uses the square root. Yeah, I get the same exact answer. The one with volume, I think the one we had to do with volume was this one. Yeah, let's do this one with volume. The sizes were, oh, let me see. Okay, so this base area over here was 32. It doesn't look exactly the same as before. That's 32. And this base over here was 200. So that, and I know the volume over here is 150, and the volume over here I didn't know. Let's call this x. I can say small is to large as small is to large. Now the problem is, what's going on here? This was a ratio of areas. This is actually k squared. This is a ratio of volumes. This is actually k cubed. How do I reconcile that? Well, think about your common denominators. If I took k squared, you have to be good with your exponents. I took, oh, alternate method. This is the scariest of them all. So alternate method symbol, okay. K squared to the third power, that would equal k cubed squared. They would both now be k to the sixth power. So to make this work, oh, you know what? I could reduce this ahead of time. I could make this, what's 32 over 200 reduced? 32 over 200, let's just call that 4 over 25. Oh, okay, that makes life a lot easier. You can do that first, right? I mean, 32 over 200 is just a fraction. This is just the same fraction. This is still k squared. This is still, so these don't really actually equal each other yet, but they will in a second. They'll equal each other as soon as I put them all in the right exponential power. So I need to take everything on this side and cube it. I take everything on this side and square it. So now we're all together in the sixth dimension. See why this is kind of alternate? This is kind of the alternate method. 4 cubed, oh my gosh. I could actually do this really quick this way. If I just took this to the third power, it would give me a nice fraction. 64 over, yeah, see, those numbers are great, aren't they? 64 over 15625 equals 150 squared, which is 22,500 over x squared. You can cross multiply. Give me a second. Yeah, look at that. We're into the, you know, what is that? 351 million. Okay, divide that by 64. Divide it by 64. We get that. And we take the, what is that? At the end, we got a number that was a square. Yeah, that's x squared. So to find, I find the square root of that, and I should get the same answer I had in the other problem. If I did that as a decimal, that looks very familiar. So that's another way to do that. It's a little scary because you run into the 100 billions and you come back. But it also works. If you're addicted to proportions and you're good with exponents, that alternate method also works. Okay, great. I'll see you in class.